So it's a real pleasure here to be talking to Dr. Bruno Tomberli with regard to his research in biophysics.
Yeah, so what I do in a nutshell is I use computers to simulate biological systems. And the exact field of application I was interested in was simulation of antibiotics, because we haven't developed a new class of antibiotics since the 60s. And the overuse of antibiotics has actually resulted in the antibiotics we have being ineffective. The basic problem, or the basic problem is it's no problem killing living systems. You know, the problem is you want to kill the bacteria, but not the host. You know, me. I got a bacteria. I don't want to die. I just want the bacteria to be dead. So we're very familiar with these. They're disinfectants. So when you get a cut and you get pour alcohol on it, the reason why it burns is because it is harming both the bacteria, good, and you, that you register as pain, bad. So what you want is you want a substance or a compound or some sort of agent that will only harm the bacteria. And what the difference is that bacterial cells have a different coating on them. So if this is one of your cells and this is a bacterium, that bacterium has a different coating. Say if it's a gram-negative, it has a lot of very hairy stuff on it like this that your cells don't have. So you can develop compounds, short peptides is what we've been working with, little basically bent up bobby pin looking proteins that will be very attracted to the bacteria and not very attracted at all to your cells. So they'll stick to the bacteria, and then because of their shape, they mess with the bacteria in some way. Very often they're pore forming. So they basically form a hole. A few of them get together and all these bobby pins kind of form like this in a circle, and they leave a hole in the bacteria and its contents leak out and it dies.
Can you actually see that happening?
Yeah, they've gotten some electron micrographs of this, but electron microscope graphs, but mostly you infer it because of you can just see the chemical concentrations of things that used to be inside the cell suddenly being, you don't register them in the instrument, suddenly you register a lot of that on your instrument, kind of thing, right? Lots of cell contents are in the fluid now, so the cells, you infer the cells must be blowing up. So the physics that interests myself and my colleagues is the why, what's called the selectivity filter. Why, what physical reasons is this funny shape more attracted, has a stronger force of attraction with this thing than with that thing? Mm-hmm. So the techniques, these are complicated systems. We don't study them at anything like the whole cell level. In fact, so we take big computers and we mock up cell membranes. Cell membrane looks something like this. So you have these water-soluble heads, and you have these long fatty acid chains. So you have a bimembrane that might be literally just maybe 100 or so molecules in size like this. This would be in 2 dimensions, so it might be like 10 by 10 this way. So you have a little patch of cell membrane. I'm just drawing this very quickly here, okay? There's your membrane, and we will take one of these little proteins, and we will just hold it at a certain height and measure the force we feel up here. Okay.
So you were talking about this
in a computer now. Yeah, I don't. This would be part of the cell. Would be gigantic, the size of this room or something. But we don't have the resources to run an entire cell membrane, right?
But you're modeling this section
a little
of it.
patch of cell membrane, and we hold this thing. We measure the force, and basically, it turns out what we want to know is the energetics of the attraction. How much energy is gained or lost for this peptide? It's called this little short molecule to wind up from up here to down here. You see, like how much energy is gained or lost in moving it from
So
here.
what's attracting or repelling it?
Yeah.
The electrostatic forces?
Electrostatic forces, yeah. Okay. There's a lot of distributed charges. These peptides are called cationic antimicrobial peptides. So they may have only 25 residues. They're short proteins. Maybe 10 of them have a charge on them. So it's a highly charged species. They're antimicrobial, and then they're peptides. They're short little protein, short little bent up bobby pins is what I think of them as. So one of the ways you could do this is you could take the force and measure it at each height. Like hold it here for a long time, measure the average force, hold it here for a long time, measure the average force, hold it here for a long time, measure the average force, and then integrate the force as a function of distance to get the work it would take to go from here to here. And that work is you can relate easily to the
Now,
binding
To
energy.
be clear, when you say measure, you mean calculate, actually.
I mean, sorry, calculate.
Okay, just to
So
double
I
check.
always think of a
Double
computer
checking.
experiment as a computer experiment. Like
Right.
I'm measuring, meaning in the computer,
okay.
I'm letting these things all follow the laws of physics in the computer, and I'm just checking what force this thing feels as I hold it here. So that's in a nutshell what I do.